Alright, we're ready to start volumes of revolution. Now the basis behind volumes of revolution is using cylinders to find the volumes of different shapes. So let's go back to cylinders for just a second, back to geometry. You should recall that the volume of a cylinder is pi r squared times h. Well, r is the radius of the base and h is the height of the cylinder. So cylinders can come in all sizes and shapes. For example, our cylinder on the left could be a can of corn, which is a cylinder. And then on the right, if we had a dollar coin, it's still a cylinder. It's a very flat, thin cylinder, but it is a cylinder nonetheless. And that's more the style we're going to use in just a minute to find volumes of revolution. So again, the volume of the coin is pi r squared h. So let's go to our first problem. Well, before we do that, let's take a look at cylinders on axes leading into volumes of revolution. The one on the left, the purple one, I've taken a cylinder and it's been rotated around the x-axis. So if you wanted to find the volume of that cylinder, again, there's only two things that you need. One of those is the radius and the other is the height. Well, the radius is countable. If you take a look at the cylinder, it's centered on the x-axis, so the radius is the distance from the x-axis to the outer edge, which is the distance of 1, 2, 3. So the volume is pi times 3 squared times the height of the cylinder. Well, the cylinder is on its side, so the height is the horizontal distance, which appears to be 1, 2, 3, 4, 5, giving us a total volume of 9 times 5, 45 pi. Similarly, the one on the right, still a cylinder, but this time it's rotated around the y-axis. So the radius is from the axis to the edge, which is a distance of 2 in this case. So the volume is going to equal pi times the radius squared, which is 2 squared, times the height. Now this height, going up and down in the y direction, appears to be 1 unit, giving us a total volume of 4 pi. So finding volumes of cylinders on axes. All right, now we're ready for our first problem. Problem number 1. Find the volume when the region bounded by, those words mean the area that's trapped in by these three things: y equals x squared, y equals 4, and x equals 0. So that's going to be a region, which you'll see in just a second on the graphing screen. We're going to take that region and we're going to revolve it around the y-axis. So let's take a look at that. Alright, here's the graph of what was on the previous. The red graph, of course, is y equals x squared. The green line is y equals 4. And it's also bounded by the y-axis, which is x equals 0. So that's the dark black one. So that gives us that area which is kind of goldenrod colored. And we're going to take that area and we're going to revolve it around the y-axis. Now for you to better visualize what's going on there, let me show you that by using this program. So here goes. And here comes the volume. Slowly but surely, here it comes. So we took that original region that was shaded in yellow and we're rotating that around the y-axis. And it is done. Now what you get, let me kind of revolve this for you a little bit. You can see you've got this shape that's kind of like the tip of a bullet. So you've gone from a two-dimensional shape to a three-dimensional object. And the object here is to find the volume of that shape. And in order to do that, we're going to use some calculus, integration, and we're going to slice that shape up into a bunch of cylinders. So let me take you back to the work page and show you how that's done. Okay, I'm going to give you a quick sketch of what we had on the other graphing screen. There are our axes. We've got this shape, and it's been revolved around the y-axis. So there's our bullet tip. Now what we're doing, we're going to slice that. Now the most important thing to remember in this whole process is you always slice it perpendicular to the axis of revolution. So we're revolving it around the y-axis, so we're going to slice it perpendicular to the y-axis. Now what that slice is, it just helps you visualize what's going on. The slice is actually, if you can think in terms of 3 dimensions, it's like that silver dollar coin. It's a very thin cylinder. So let me come over here and draw that slice. There's the slice, little thin cylinder. So we want to figure out how to find the volume of that. Well, that dot represents the y-axis. The distance from the y-axis to the outer edge of the original region is the radius of that cylinder. Now the height of this cylinder is that little tiny height, and that, being vertical, it's going up and down, so it's going in the y direction. We're going to call that dy. Right. And what we're going to do in order to find the volume, very similar to areas that we did in the last video, we're going to use an integral, and we're going to integrate that from the bottom of the bullet tip, which is at 0, to the top of the bullet, which was at 4, and the volume of the cylinder, again, pi r squared, so it's pi r squared, we'll figure out what r is in just a second, and then the height of the cylinder is dy. Now everything must match in terms of variables. The 0 is the y value of the bottom point. The 4 is the y value of the top point of the bullet tip. dy is the height of the little thin cylinder. So our radius must be in terms of the variable y. Well, the radius is the distance from the axis to the outer edge, which is the curve, the original curve. Now remember, the curve was y equals x squared, but we have to solve that for x in terms of y. So I just take the square root of both sides. X equals the square root of y. So the radius, the distance from the axis to the outer edge, that distance is represented by the square root of y minus 0, or just the square root of y. Alright, after all that, there's our integral, which we can evaluate to find that volume. Well, the rest of it's really pretty easy. The setup of the problem is the hardest part. So let's integrate this. Well, if you square y, the square root of y squared, you end up with just y. Now the pi, I always say, kick it out front. It's a constant. So this integral is the same as pi times the integral 0 to 4 of y, because the square root of y squared is y, dy. And now we integrate. Well, to integrate that, we get y squared over 2 from 0 to 4. If you sub 4 in, we get 16 over 2, which is 8. If you sub 0 in, you get 0. 8 minus 0 is 8. And don't forget, we kicked pi out front. Let's bring pi back over. So the volume of the bullet tip is 8 pi. There you go. That's your first volume of revolution problem. It's probably a little overwhelming, but they get easier with practice. We'll take a look at another one in just 1 second. This second example is just a little bit different. Find the volume when the graph of y equals the square root of x plus 2 in the interval, that just means between 0 and 4, is revolved around the x-axis. Okay, now I'm going to use the graphing program just to help you visualize the situation. You really don't need to do this. You could do this by hand and figure it out and kind of draw a little sketch and see what it looks like. But let's go to the graphing screen. Since I've already got this set up. Now the red is the graph of y equals the square root of x plus 2. And what we're going to do is first we have to find the region. The region is under that curve from 0 to 4. So let me put that in. Okay, there's the area. The area under the graph y equals the square root of x plus 2 from 0 to 4. Now we're going to take that region, that area, and revolve it this time around the x-axis. So let me get the program to do that for us. Now around the x-axis is the same as around y equals 0, so that's what I'm using on the program, and here it goes. Here it comes, spinning around. Kind of cool how this works. Alright, there is our volume. Now let me rotate this a little bit so you can see it a little bit better. It's not quite a bullet, it's like a bullet that's been chopped off on the very tip. It's kind of a bowl shape. But when I rotate it in this direction, you can almost see those individual cylinders. So those little thin cylinders that we find the volume of each one and we add them up through integration. So there's our region. Let's go back to the drawing board and see what the heck's going on. Alright, let's have a little quick sketch of this. Our original region looks something like that. We revolved it around the x-axis and we ended up, that's not too good, but we ended up with a shape that looks like this. Now the trick in setting these up is you only focus on the original area before we revolved it. You only have to look at that part of it to figure out how to set it up. But as I said on the last problem, the most important point is to remember you always slice it perpendicular to the axis of revolution. Well, this time we took that red area and we revolved it around the x-axis. So the axis of revolution is the x-axis, so I'm going to slice it that way, up and down. Alright, so this time we have a little thin cylinder. Let me see if I can kind of sketch that. Here's our silver dollar on its side. So, to find the volume, we need to know mainly one thing, and that one thing we need to know is what is the radius. Well, the radius is from the axis to the outer edge. Now the thickness of that coin, that little thin cylinder, this time the thickness is going left and right. It's going in the x direction. So this integral is different. Whichever direction the thickness is going in, that is the variable we want to use. So to set up the integral, remember it's pi r squared, and then d variable represents the thickness. Well, this time, as I said, the thickness is going left and right, which is in the x direction. Now we have to figure out what r is. Well, r is the distance from the axis to the outer edge of the original area. And what is it hitting up there? Well, it's hitting the curve. And the curve is the square root of x plus 2. So let's fill that in. The square root of x plus 2 squared, because it's the radius squared dx. Alright, everything's well, fine, and good except for the limits of integration. Again, those must be x numbers. Everything's in terms of x on this problem. Grab my highlighter here. There's an x, there's an x. So those two numbers, the limits of integration, must be x numbers. Well, looking back at the picture, what is the smallest x value to the largest x value? Well, the smallest x value starts here, and it goes all the way to the end of the bowl shape, which is over at 4. So the limits of integration are from 0 to 4. All right, to do the integral, again, kick pi out front. To simplify this a little bit, the integral from 0 to 4, the square root of x plus 2. I would probably FOIL that out, and we get x plus 4, radical x plus 4. Okay, now a little exercise in integration. I'm going to keep that pi out front and increase x squared over 2 plus 4x to the 3 halves over 3 halves, which is the same as times 2/3. Let me stick that in there. Plus 4x. Let's clean that up just a little bit, create a little room here. Pi still sticking out front. X squared over 2 plus 8/3 x to the 3 halves plus 4x. And our limits of integration are 4 down from 0. Alright, sticking 4 into the expression, 4 squared, 16 over 2, that would give us 8. Now, 4 to the 3 halves. That's not as hard as it looks. That's the square root of 4, which is 2 cubed, which is 8. Now we're taking that times 8/3, so 8 times 8/3, 64/3. And then 4x. 4x is 4 times 4, which is 16. That looks like a grand total of 24. 8 plus 16, that's 72/3, plus 64/3 is 136/3, if my arithmetic is working. And thank goodness we have a 0 on the bottom, so that gives us 0. So we end up with a total of 136/3. And don't forget our little pi friend over there. Volume 136 pi over 3. Again, not the easiest example in the world, but if you understood those two examples, you can do just about any type of problem dealing with volumes of revolution. We'll take a look at more. So let's try one without using the graphing program at all, just to see if we can handle this by hand. So taking a look at this third example, what we're going to do is just kind of draw a little sketch, and that is not too difficult. Y equals the square root of x is our graph, and you should be familiar with what that looks like. Now we want that graph from 0 to 2, so what I'm going to do is put some coordinates in here. If x equals 0, we know y equals 0, that's our left endpoint. If x equals 2, there's 2. Our y value would be the square root of 2, so the coordinates at that point are 2 comma square root of 2. Alright, what we're going to do is take that region and revolve it around the x-axis. So let me show you the region. Here's what we're talking about. The region underneath that curve. And we're going to revolve it around the x-axis. Now you don't have to, and eventually I'll encourage you not to because it just makes it more confusing. You don't have to show the region after it's been revolved. But I'm going to go ahead and do it. I'm going to kind of dash it in here. If you took that yellow region and revolved it around the x-axis, you'd end up with our friendly bullet tip again on its side. So there we go. Now, next step, slice it perpendicular to the axis of revolution in red. All right, now remember, three-dimensionally, that is a thin cylinder. little thin silver dollar cylinder. The thickness, the height of that cylinder is going again left and right. So that means that the integral is in terms of x because it's left and right. That's the height of the cylinder. The only remember, pi always gets kicked out front, so we'll just go ahead and kick him out. And the only thing left to do in the blank is what is the radius, and we'll square it. Well, the radius is the distance from the axis, where the red dot is, to the outer edge of the original area before we revolved it around the axis. So, how tall is that? Well, it's hitting the curve. And the curve is the square root of x. So that distance is the square root of x. That is that distance. So I fill that in for the radius, the square root of x, and we'll square it. Now my limits of integration are the x values from one end. So where that red dot is, that's 0. To the x value at the other end, that's 2. And this one's ready to go. A much simpler integral this time. Let's see how fast we can do this. Pi out front, 0 to 2, square root of x squared is x, dx. Integrating, don't forget pi, we'll kick him out, leave him out. Increase over increase, 2 to 0. Sub a 2 in, and you get 2 squared is 4 over 2, which is 2. Sub a 0 in, and we get 0. Subtract those two values, you get 2. And bring our pi that we kicked out, and there's the answer. Boy, that was fast, fun, and easy. Alright, the end of the first video on volumes of revolutions.